guys, this is Mr. Chase, and today we're going to be talking about reactions in solution. Specifically, we're going to classify reaction types as well as focusing a little bit more on redox reactions. So, getting started today. First off, it's important that we understand what the objectives are for the day. What we want to be able to do is classify reactions based on the evidence that we see when they're mixed. Also, we should be able to understand that reactions can be classified in more than one way. We'll be assigning oxidation numbers to atoms for any compound, element, or ion, and we should be able to identify which species in reactions are going to be oxidized and reduced. So to make a connection here to our AP content, there are several different sections that are going to connect. First off, being able to write equations, so molecular, ionic, or full ionic equations, those are going to be important. In addition, we need to have all the different reaction types. So we have synthesis, decomposition, combustion. All of these things are explicitly mentioned in the AP curriculum, and that's what we're learning today. In addition to that, we have our redox and evidence of chemical change. That's AP section C. Production of light, color changes, things like that. We're going to get into all that stuff today. Now, our first reaction type is synthesis. Synthesis occurs whenever you have two separate particles, and those particles are going to react to make one more complex thing. So here we have an example of iron with oxygen gas. They combine to form iron 3 oxide. Now here's our balanced chemical equation, but just to give kind of a feel for this, remember that iron as an element is going to be solid, oxygen will be a gas. As these come in contact with each other, they're going to make the iron 3 oxide, which you're probably familiar with. It's just rust. Okay, so again, synthesis, two things or more combining together to make one more complex product. Next we have decomposition, and you can think of decomposition as kind of the reverse, the opposite of a synthesis reaction. Instead of two things coming together to make a complex thing, it's one complex that's splitting into multiple parts. So an example of a decomposition would be the electrolysis process. When water decomposes into its parts, hydrogen and oxygen, as you pass electricity through that water. Now here's our chemical equation, and again we're just starting with water, regular water. But that water, again, it's bound chemically. So we can separate it in this process. Again, applying this electrical field, what we're going to see is that our hydrogen and oxygen gases will separate out, and this was one of the key evidences that we found to understanding the nature of water, because you can tell that the volume of oxygen in comparison to the volume of hydrogen is in a 1:2 ratio, which you'll notice is our coefficient ratio in our reaction. Now, let's continue on to talk about replacement reactions. Our first is the single replacement reaction, single replacement. This occurs whenever you have an element replacing a similar ion that's part of a compound. So you'll have an element, you'll have a compound pair, the element will replace one of those ions, make one of the existing ions into its own element. Now a visual of this would be silver nitrate solution reacting with copper metal. Here you see we have our copper nitrate. And when you see copper with nitrate, you know those are paired. You know that this is an ionic substance. So here's our positive and here's our negative ion in this solution. What we'll do is we'll introduce a copper ion, and that copper ion is going to be essentially more reactive. It's more attractive, you could think of it this way, when compared with silver. What this does, it allows copper to go from its element, its neutral form, into its charged form. And in the process, it's going to give an electron to the silver, making that silver the neutral thing now. The nitrate, still hanging out, just doing its thing, not having any effect here. Now, visually, this is what's taking place. Our silver nitrate that we see here, it's a colorless solution, but we know that there are silver ions present and there are nitrate ions present as well. When I mix the copper in with that solution, what we're going to start to see is this. First off, this reddish metal, which is of course the copper metal, it starts to, it'll get darker at first, and then all of a sudden you'll start to see these bright flakes forming right off the copper. Well, that's because these silver metal particles, the solid silver, are forming right on the surface. As they're forming, remember, copper ions are forming. And when we look here, we can see those copper ions have a bluish hue to them. Now, technically they're copper too. Suspend your disbelief. It's copper ions, okay? Now, we've learned about single replacement. Now I got to hit double replacement. And you should be very familiar with this already because this is what we learned as we were starting to talk about net ionic equations. In a double replacement, you have one ion pair and another ion pair, and they're going to switch partners, essentially, so that the positive of one compound joins with the negative of the other compound, and vice versa. So our example here would be the reaction of lead nitrate and sodium sulfate solutions. We have our lead nitrate, our sodium sulfate. They're going to do that swap. At first, the lead nitrate we see right here, it will have those lead 2 ions. It's going to have our nitrate ions present. Here we have our sodium ions, and there would be sulfate ions present. When they mix, what we end up seeing is that nitrates and sodium, as we know, these are always soluble. They're not going to come together. They will not form a precipitate. But our sulfate ions are generally soluble, and lead 2 ions are an exception to their solubility. So that makes a precipitate. That makes a solid. Right here, this white kind of, I don't know, powdery looking thing that's in the solution, that's our precipitate that's been formed. That is our lead 2 sulfate as a solid. What we still have present in the solution, though, would be those sodium ions as well as the nitrate ions that are moving around in there. All right, let's move on to combustion. Now, combustion, whenever we hear combustion, we typically are thinking about big, violent, crazy explosions and fire. And that's true. But let's make sure that we understand combustion from a chemical perspective. So we have oxygen reacting with any other substance. That is combustion. Now, the combustion that we typically see in terms of a chemical reaction, we focus on reacting with hydrocarbons. So these are any compounds that have hydrogen and carbon in them. And the evidence that we see of this reaction is going to be energy given off in the form of light or heat. You would see fire, okay? Common products would always be water and carbon dioxide. So let's talk about methane. Methane gas, which you may or may not know, are cow farts. Methane gas is going to burn in air. Now, whenever you see that it burns in air, we're referring to this combustion reaction. It means that this methane is going to combine with our oxygen gas that's found in air. So, this is our chemical equation, the chemical reaction, and it's important that we understand that. Before we do, moment of levity, remember these are cow farts. Now, this is our visual of what's taking place in terms of the molecules. But when you look at it, here's the thing that kind of trips us up. Methane is a clear gas. Oxygen is a clear gas. Carbon dioxide, another clear gas. And then we have water vapor, another clear gas. So the evidence of this reaction, if it is in fact complete combustion, is gases are turning into other gases and you can't see them. So we have to look at other evidence. What we would see would be that flame, okay, that burning, that energy and the light given off. In addition, what we could do is we can collect the particles and we can test for what particles have been collected, those carbon dioxide particles or the water vapor. And we'll be talking more about that in a little bit. So now that we've seen combustion, it's time to get into the coup de grace, the oxidation and reduction reaction. So our redox, this is a very common process and it occurs in a lot of other reaction types. So anytime electrons are lost or gained by chemicals, there's a redox process that is taking place. Okay, so it's all about loss of electrons and gain of electrons. Now we have a nice little mnemonic to help you understand what is being reduced and what is being oxidized, and that is Leo-Ger. Leo the lion says Ger. If you lose electrons, that is oxidation. Leo. And then Ger, if you gain electrons, this is reduction. Okay, so Leo, Ger. There are other mnemonics that we use to help remember this, but losing electrons, oxidation, gaining electrons, reduction. Our example equation that we're going to talk about would be the reaction of lead-2 oxide combining with carbon to form lead metal and carbon monoxide gas. So as we translate that, as we write that out, we're going to see that is our lead-2 ion here with oxygen, carbon as an element, we have lead as an element in our product form, and then we have carbon monoxide, so we have a molecular gas that's coming off of this thing as well. So what we're going to do is just kind of analyze, take a look at what's taking place here. We had lead right here combined with oxygen, so we know that that is the lead-2 ion. And that lead-2 ion is going to turn into a neutral element. So the only way for a 2+ ion to go back to being neutral is if it gains those electrons. It became stable in the first place to become an ion by losing electrons. Now it's going to gain some electrons to become a solid again. So gaining 2 electrons, that's what's taking place there. Well, if we follow our Leo Ger, we know that gaining 2 electrons, well, is that going to be an oxidation or reduction process? Gaining electrons is reduction. Now we'll focus on carbon. Our carbon begins as a neutral element. So remember, it's uncharged. It's a 0. It is going to go over here, and it's going to bond with carbon and oxygen. These two things will come together. The tricky thing is that carbon and oxygen are both nonmetals, so it's not as cut and dry when we talk about the shifting of electrons. What has to take place in this process is the carbon is going to have to lose electrons in order to bond with the oxygen. Okay, and remember, oxygen, it wants to be stable, it wants to combine, right? So what happens in this process, once again, is a loss of electrons. And if we follow our mnemonic, remember, Leo Ger, lose electrons, oxidation. So our lead-2 is reduced, our carbon is oxidized, and then when you look at oxygen here, it maintains the same oxidation state. So it's a 2- charge. It stays with the 2- oxidation state. It is unchanged. Now, I kept referring to oxidation states. Something that we have in order to help us understand these better, to make comparisons a little bit better, to quantify this, is we have oxidation numbers that can be assigned to any compound, whether it's ionic, whether it's an element, or whether it is combined as a molecule. So let's talk about that now. These oxidation numbers, they help us figure out which atoms lose electrons, which atoms gain electrons. So another context of oxidation and reduction is this idea that if a substance is reduced, what that actually means is that the oxidation state is going to go down, right? It's reduced. That's why we call it reduction. The state of oxidation is decreased, reduction. So of course, if your oxidation state goes up, that would be oxidation. All right, so hopefully we get that idea. But let's make it visual. Let's see what's going on. First, we can assign oxidation numbers to any uncombined elements or ions. Uncombined elements always get a 0. Ions will get their charge. So, carbon, we have a 0. Lead on the product side would also be 0 because these are both uncombined elements. They're neutral. Okay? Now, the oxygen here in our lead-2 oxide, that oxide ion, remember it's charged. It has a specific charge, and ions have an oxidation state that is equal to their charge number. So we're going to assign oxide a -2 oxidation state. In order to balance that out then, we know that our lead-2 ion must have a +2 oxidation state, and when combined we notice that this compound is neutral in terms of its overall oxidation. Next we have to look at our molecular compounds, and molecular compounds are actually not that bad. What you'll do is you're going to look at the electronegativity of the atoms that are present. Whichever atom is the most electronegative is going to be treated as if it's an anion. So here in carbon monoxide, We have carbon and we have oxygen. And oxygen has the higher electronegativity. Oxygen will be treated as though it were an oxide, and it gets an oxidation state of -2 again. Now, in order to balance the overall charge, the overall oxidation state, that means that this carbon must no longer be in a 0 oxidation state. It must be up in a +2 oxidation state. So now that I've assigned all of my numbers, we can compare the elements as reactants and products to see, are we increasing or decreasing our oxidation states? The lead goes from a +2 into a 0 state. Well, +2 to 0, that must have gone down. It is reduced. Our carbon went from a 0 to a +2 oxidation state, so it's increased. That must be oxidized. So we're going to be spending more time on redox. This was our introduction right now, and especially as we get into AP chemistry, redox reactions play a vital role in a lot of processes. Okay? When we do several reactions, what we've already seen is gas formation and precipitation. Well, let's focus specifically on precipitation as a subtype of a reaction. Precipitation is when a solid is formed from that ion swap we had talked about. The example we'll use is barium acetate reacting with sodium sulfate. So we see this, and at first it looks really daunting, it looks really scary, but let's try to paint a picture and see really what's happening in solution here. In the beginning we have two separated solutions, our barium acetate and our sodium sulfate. Well, these are two colorless solutions, so it helps if you break it down and try to think what are the ions that are present. Here in beaker A, we would have the barium 2+ ion, and we also have to have the acetate ion. So these are present in solution. They're going to be moving around doing what they do, right? In our solution B, we'll notice that we have sodium ions present and we would have sulfate ions present. And so kind of like what we looked at before when we were talking about these double replacement reactions, when combined we would typically see a solid forming. So as we notice, remember that sulfates are generally soluble. However, the barium 2 ion is one of its exceptions. So this would have to be our barium sulfate solid. And then in solution, remember, we still have those ions. We still have sodium ions present, and we still have our acetate ions present in that solution. So now we move on to neutralization. These are also known as acid-base reactions. Neutralization is whenever a proton is transferred from an acid into a base molecule. Typical products would be a salt as well as water molecule. Okay, so that salt doesn't have to be sodium chloride, it's any ionic compound. We have hydrochloric acid as a starting point and potassium hydroxide. Now remember, hydrochloric acid, this is actually ionized. It's not going to be a molecule in solution. And it is going to be combining with potassium hydroxide, which is, again, ionized. It's a strong base. So if I look at this visually, I have another clear solution and another clear solution, and I mix them. It makes water molecules, another clear liquid, and then sodium chloride in solution. Potassium chloride, hey, well, that's a little fix we can make. There you go. So when this comes together, when we make this, it's going to be hard to visually see it taking place. So we're going to have to test by some other means. And one of the common things that you see in these neutralization reactions is they're going to give off some heat. Right? That's one of the other products. So if we had a thermometer, we could test the amount of heat generated. That's one way to get evidence of reaction. Another thing that we could do, we could add a chemical that is sensitive to the hydrogen or hydroxide concentration. So we can tell that the hydrogen is being used up or the hydroxide is being used up as it neutralizes. In addition to that, we have a very specific technique that we use known as a titration. A titration allows us to mix an acid and a base and generate some data based upon pH changes that's really kind of interesting and very informative. So the general setup, the apparatus here, is you have a long cylinder that is typically filled with either the acid or base, your choice. So I'm going to choose the base. In this container down on the bottom, we have our known acid. We know the amount of that acid, but we don't know the molarity. For my base, I know both the molarity and I'm going to add a very specific volume so that we completely react away the number of moles and we can find out the number of moles of acid. So this, again, is known as a titration. The purpose of that titration is to identify an unknown solution's molarity. The pH curve that we see generated here, you'll notice that in the very beginning, this acid, we have our pH probe connected there. This acid is going to have a very, very low pH. Over time, as I start adding more and more of that hydroxide solution, though, my pH will rise, and it's going to hit a steep slope. And in the very center of that steep slope, we find this point that we call the equivalence point. Now, what's so special about the equivalence point is this is where the number of moles of our acid are equal to the number of moles of our base. So there's a lot more to be said about this, but this will serve as a good introduction to these neutralization or acid-base reactions. The last thing that we have here are the tests that we could use to identify a gas. So first off, we'll be using a candle or a match to make these tests. The first test is to determine, is hydrogen gas present in our solution, hydrogen? I'm going to give you the opportunity to take a peek at some of these videos. So first off, we have the hydrogen gas in a combustion situation. I will skip to the portion that actually matters. Let's get up here. So we have collected some gas, and now what we're going to do is we're going to light a match and detect, is it in fact hydrogen? Alright, so again, there was that kind of quick popping right there at the end. There we go, that little bark, that pop. So this is evidence of hydrogen gas. Hydrogen is a highly flammable gas, and if you add a candle or a match, a splint to it, you get this rapid pop, this combustion. So one way to test for a gas, that's the hydrogen gas. Next, oxygen gas is another one of our common products that we would see. So our oxygen, if you take a look right here on the left, I'm going to show you that guy. There are a lot of examples that are given in this video, so I'm just going to run through a few of them. Here we have a flame before it is connected with the oxygen inside this flask. And there it is. Now it's hit the oxygen pocket, and you get this big bright flame, this large glow that's taking place. Alright, the last bit that we have here is carbon dioxide gas. We can tell that there's carbon dioxide because it will put out a candle. So that's it, guys. That's all I've got for you. I know it took a little bit of time, but hopefully this all made sense to you. You'll be able to review it a little bit later. And if you have specific questions, please ask me.